Hello everyone. So in this video here, we're going to discuss the reduction of alkynes. And this is from section 9.5. Section 9.5 in the textbook. Okay. And we're going to see three different scenarios here. Okay. We're going to see, and we'll do them one by one. Okay. So the first one we're going to see here is conversion of alkynes to alkanes. Okay. And this is catalytic hydrogenation, similar to alkenes. Okay, so this is very similar to alkene hydrogenation. So essentially what happens here is when you start with an alkyne, okay, alkyne, and you react this with hydrogen gas. And again, I think one thing I want to point out here is, since we're using gas, there's a lot of it. And let's imagine that there's excess gas here. Okay, so there's not just one equivalent of hydrogen gas, but there is excess gas here. And pretty much in these reactions, when we pressurize the system with hydrogen gas, there is always an excess, of the gas, the hydrogen species here. So there's like a lot of hydrogen gas around. So what happens here is when you do this reaction, hydrogen is going to add to the alkyne. And when it adds to the alkyne, this is again a cis-alkene addition. So we should get an alkyne where the hydrogens have added. And what we get is an alkene product here. But what we know from the reaction of alkenes is that alkenes also react with hydrogen under these conditions. So that means the reaction doesn't really stop here, okay? So you get an alkene, like an intermediate, but this basically keeps going. And then your final product is basically an alkane, where you've added two hydrogens to the alkyne. You added basically two hydrogen molecules. Okay, so two sets of two hydrogen molecules basically. Okay, so you've done this twice over essentially, and so this keeps going, and your final product is going to be an alkane. Now, under these conditions, it is really hard to prevent this reduction, the second reduction, to stop at the alkene, because you have a product which is also a reactant under similar conditions. So it basically keeps going. So it doesn't stop, it just keeps going. So for any alkene that you can think of, so let's say if we have this 1, 2, 3, 4, 5 carbon alkene. So this is one new nomenclature. So pent 1-ine. If I take pent 1-ine and if I do a reaction with hydrogen gas, now this 2 may or may not be written all the time, but just realize that when we have this gaseous species, imagine like a lot. So when you have one pent 1-ine or one pentyne, you do this reduction, our product is going to be 3, 4, 5 pentane. So we're going to get our alkane as the product. Okay, so that's the catalytic hydrogenation mechanism. Is very similar to the catalytic hydrogenation of alkenes. Okay, so that's one of the scenarios here. But the big question here is, or the important thing here is, okay, we have an alkyne which has a functional group in it, which means we can actually do some reactions on this alkyne. But if we do this hydrogenation, if we go all the way to an alkane, we've lost functionality here. again, realize that for an alkane, the only reaction that you can do on an alkane is that free radical halogenation. The only useful reaction that we know of, okay, is the free radical halogenation. So this may not be a very useful thing to do. Instead, I think what we might be, or what chemists are often interested in, is to actually stop at the alkene somehow, okay? That you want to start with an alkyne, but stop at the alkene, not go all the way to an alkane. So we're going to look at two strategies for doing that, okay? And to get there, you know, so what we want to do is this here, stop at the alkene. Okay, and when you think about it, so we want to go from an alkyne to an alkene. Okay, we want to go from the alkyne to the alkene. And so we will come back and fill in what is it that we need to do here, okay? We'll go from an alkyne to an alkene. In fact, I'm going to change my alkyne a little bit here. Let's use a different alkyne. Let's use an internal alkyne. So let's say that's the alkyne. What we want to do is we want to do a hydrogenation. We want to do a hydrogenation, and we want to stop at an alkene, let's say. We're going to stop at an alkene. And since this is a syn addition, that means the hydrogen adds from the same phase. I've drawn the cis-alkene. So in this particular case, the alkene that's formed is a cis-alkene, okay? Cis-alkene is our product. So the question is, how would we do this? What sort of modifications do we need to bring to the system so that we are able to do this, this hydrogenation? And again, think about it mechanistically. When we have an alkyne, and if we have some sort of a catalyst, okay, we have a catalyst, the hydrogen is going to interact with the catalyst, get attached to the catalyst surface. Alkyne would come, interact with this catalyst with the hydrogens on it. The hydrogens would add from the same phase, and we get the cis-alkene. But what we know is the catalyst that we're using can also hydrogenate alkenes. So that means another molecule of hydrogen comes, it basically interacts with the catalyst, gets added to the catalyst surface, and then the alkene comes in, the hydrogens add from the same phase, and we get to an alkane. That is what's going on in the catalytic hydrogenation that we just saw. And what we want to do here is we want the reaction to stop at the alkene stage. And so if you think about it, I think what we want to happen here is we want a catalyst which would interact with the hydrogen. The hydrogen is going to come and add to the catalyst. The alkyne would come and interact with this catalyst with the hydrogens on it. Hydrogens would get added to the catalyst. They would make the alkene. But after that, we don't want this alkene to interact with the catalyst anymore, because if the alkene can come and interact with the catalyst that has hydrogens on it, then the hydrogens would add to the alkene as well. And then we're going to go to an alkane. But we want to avoid that step, okay? We want this reaction to stop at the stage where the hydrogens have added to the alkyne and we get the alkene, okay? So the way we do that is to use a catalyst that's partially modified, and this is called a poisoned catalyst, okay? So you basically add some things to the catalyst so that the catalyst has a preference. The catalyst would like to interact with the alkyne, but it would not want to interact with the alkene. And when you think about it, it should be feasible, it should be doable, because the alkyne has 2 pi bonds, so there's a lot of electron density over there. Compared to an alkyne, the alkene has lesser electron density. The pi electron density is less. Okay, so there is a difference in electron density between the two. So this is possible. We'll not go into too much detail here, but the two catalysts that actually allow us to do this, one is called the Lindlar's catalyst. Okay, this is a Lindlar's catalyst. There are several variations of this catalyst. One variation is where you have palladium, and this is on a support of barium sulfate. And then there's an organic compound added here, which is called quinoline. Okay, so quinoline's added to this catalyst mixture. So all of this basically serves to act as a poison for our original palladium catalyst, because if we just use palladium, the alkyne is going all the way to the alkane. That does not happen with this combination here. So this is one combination, or there is a simpler version or a simple thing to remember, which is nickel boride. You can use nickel boride for doing this. Let me verify something here. Sorry, Ni2B, okay, my bad. Ni2B is the catalyst. Nickel boride is another catalyst that we can use for doing these reactions, yeah. So nickel boride is another catalyst that we can use. So any of these combinations would actually help us convert an alkyne into the cis-alkene, okay? Because they would prevent this further hydrogenation that happens. So let's look at an example quick again. You know, these are not that difficult of a reaction. So let's look at an example here. So let's say if we have an alkyne which has ethyl groups on both sides, and if we take this catalyst alkyne and we do hydrogen, and let's say if we do Ni2B, nickel boride, so we're using a poisoned catalyst, and the hydrogens are going to add in a syn fashion to these alkynes. And so this is 1, 2, 3, 4, 5, 6. So this is basically hex 3-ine. That's where the triple bond is. So now what we should get is a cis-alkene where the double bond is on the third and between the third and the fourth carbon. So what we're going to get is we'll get 1, 2, 3, double bond, 4, 5, 6. And we get hex 3-ene, and this is the cis-alkene. So we get 6 cis hex 3-ene. So the hydrogens add from the same side. So we get a cis-alkene. Okay, so that's one of these reductions using the poisoned catalyst. Okay, so here basically the way we do this is by using a Lindlar's catalyst or nickel boride. Okay, either one of those two combinations would give us the cis-alkene. Okay, that would give us the cis-alkene. And so then that raises then another important question. Okay, so then how do I make a trans-alkene? Can I start from an alkyne and make the trans-alkene instead? You know, I don't want to make the cis-alkene. And now when you think about it, that naturally should require a different mechanism, because if we use these catalysts, you know, similar to the palladium platinum or any of this poison catalyst, they're always going to give us the cis addition or the syn addition of the hydrogen, and we don't want that. We want to get a trans-alkene. So that's this third method where we're going to convert an alkyne into a trans-alkene. And for doing this, we use the dissolving metal reduction. So we use metals that are dissolved for doing this reduction. And The simple scheme here is if you have an alkyne and if you react it with sodium metal, okay, so this is sodium, comma, ammonia liquid, okay, sodium metal in liquid ammonia, okay, and this reaction is done at low temperatures usually, okay. So when we do this reaction, we are going to get the trans-alkenes, and now the two hydrogens add from opposite sides and we get the trans-alkene, okay. So we'll look at the mechanism of this reaction. How does this reaction work? You know, how do we get this trans-alkene? So, before we get there, what I want to mention is this combination of reagents, okay? What it does is sodium is a very electropositive metal, okay? So when it's in this solvent, liquid ammonia, it actually generates electrons. It ionizes, okay? It ionizes, and so this would essentially give us sodium ions, Na+, plus it's going to give us electrons. And these electrons are in this liquid ammonia. So it gives us sort of electrons that are solvated by the ammonia solvent, okay? And so we get sort of free electrons, you know, so we have a metal which can actually separate from its electron and become an ion and give you an electron. And that is what's helpful here for doing this reaction. So when we mechanistically, the way we understand this is you have the alkyne, and in presence of this electron, that's a single electron, that electron brings in that electron comes, one of the pi bonds in this alkyne splits open, and one electron goes with this electron that's coming in, the other electron goes to the other carbon atom. And so what this gives us is what we call a radical, called a radical anion. Okay, so it's a radical anion. So we get a radical anion because we have a radical and then we have an anion. So we have a negative charge over there. Now when this radical anion is formed, this goes into this trans geometry, because if these were cis, then the two electron sets would actually repel each other, because the radical is an electron, that's electron density, the negative charge is more electrons. So if they were both cis on the same side, then they would cause repulsion. So to avoid that, this radical anion adopts this trans geometry around this double bond, okay? And once we have this, what happens is the anion part here, the negative charge, it goes and deprotonates ammonia. It takes a proton from ammonia, okay? It takes a proton from ammonia, and that would give us now a radical. Okay, so this gets a hydrogen and we've got a radical over there. Then another electron from the sodium and liquid ammonia that comes in, they combine to give us another anion. Okay, and then finally this anion deprotonates another molecule of ammonia. Okay, it grabs proton. Okay, when it deprotonated here, you're going to make NH2 minus, sorry about that. So it's going to deprotonate again, and what we get is an alkene where the two hydrogens were added in a trans fashion. Okay, so we get the trans-alkene here. And the reason we get this trans-alkene is because of the formation of this radical anion where the trans geometry was set because of the repulsions between the electrons. Okay, so that's the mechanism of the dissolving metal reduction, or the sodium ammonia reduction, okay, whichever way you want to call it. So now if we think about it, if we have that same alkene that we had earlier, and if we do this reaction with sodium and ammonia liquid at low temperatures, what we're going to get is we will get the trans-alkene now. So this is hexyne again. Okay, so this is hex 3-ine. And what we have here is trans hex 3-ene. Okay, so we get the trans-alkene. So this way, starting from an alkyne, we basically have the choice of making an alkane. Then we can use hydrogen and then just a catalyst, platinum or palladium. Or we can start from an alkyne and use Lindlar's catalyst or nickel boride and make the cis-alkene from it. Or we can use sodium and liquid ammonia to give us the trans-alkene. So we have we basically have the choice of making all three possibilities here. Okay, so that is the catalytic hydrogenation of alkynes. Find this in section 9.5. That's where all of it is. Okay, bye.